Hey class, this is Juan Ramirez with EE 2715, Linear Circuits 2, Transients. Now we're going to get into a new chapter of the Fundamentals of Electric Circuits book where we look at applications of the Laplace transform for circuit analysis. That's chapter 16 of that book. We'll start by looking at the first section, chapter 16.2, on how we could actually represent circuit elements in the S domain or the Laplace domain. That's the first step, and then once we do that, then we're able to convert a time domain circuit into the S domain completely, and then you can analyze it in the S domain. And once you have the values that you're looking for, then you can convert them back to the time domain. This is especially useful for transient behavior of circuits. So we can represent circuit elements in the S domain for circuit analysis using Laplace transforms. And we'll take a look at different elements that we will convert to the S domain. So the very straightforward ones are the actual value of voltage and current, as well as a voltage source and a current source. In the time domain, we represent a voltage source with a lowercase v. We simply represent that voltage with a capital V in the S domain. But for an actual voltage source, usually it'll be like an input, like a step input or a impulse input or a ramp input. The associated value for the Laplace domain voltage will be just the Laplace transform of that input time varying function. Okay, same goes for the current source. And we do the same thing to convert a current source function that's with respect to time into the S domain. So now we start to talk about a different concept called impedance. We talk a lot about impedance when we're looking at circuits that are AC, alternating circuit or alternating current circuits. But we could also, and kind of have to also, look at impedances for transient circuits that we are planning to analyze using Laplace transforms. Impedance, which we denote with a capital Z, is the ratio of voltage to current. We represent impedance with a capital Z equal to V over I, like so. And we will represent RLC components in the S domain with impedances. We typically assume 0 initial conditions. That means 0 initial current of a inductor and 0 initial voltage of a capacitor. As we analyze more complex circuits using Laplace transforms or in the Laplace domain, at that point you do have to represent those circuits with initial conditions that are non-zero, and that requires a little bit more effort and adds, again, more complexity to the analysis. For now, we will disregard that. So let's represent the resistor as an impedance. It's awkward. So what's the fundamental equation for a resistor? That equation is V equals IR, right? Ohm's law. So now what if we convert that into the S domain using what we just learned? The time varying voltage we just represent with a capital V for the S domain. R is a constant, so nothing's going to happen to that. Time domain current we represent with a capital I. And if we want to look at V over I, which I guess something I forgot to do was write this out. Impedance in the S domain is equal to voltage in the S domain over current in the S domain. Kind of rewriting what we wrote above, but specifically for S domain values. So we're going to solve V equals Ri such that we look at V over I. So I divide by current on both sides and I end up with R equal to V over V of S over I of S. That is what I will call my impedance for a resistor. It's equal to R. Okay. So again, you take Ohm's law, convert the voltage and current functions, because those are time varying, convert them into the S domain, and then you simplify or solve for V over I. Whatever is left, or whatever that's equal to, is the impedance associated with a resistor. In this case, it's just the resistor value. It just keeps the value. That also means a resistor does not vary with respect to the value S. Alright, now let's look at inductance. So we look at an inductor, has a value L, has a current going through it and a voltage across it. Now what's the equation for the inductor? By now we know that pretty well. It's V equals L di dt. If we convert those values to the S domain, we end up with a Vs is equal to L times, and then the rate of change of current, so it's a derivative and you have to look into your Laplace transform properties, but you end up with S times I minus the initial condition of current actually in the time domain. So plug in time 0. Okay, but now assume I of 0 is equal to 0. That's how we're going to represent the components for more simple circuits, assuming the initial conditions are 0. And if you do that, and you solve for V of S, you end up with Z equal to V divided by I, which is SL. As long as you assume the initial current is 0. Okay, now we're going to finally look at the capacitor. What's the equation for the capacitor? The equation for the capacitor is I equal to C dV dt. And if we convert that into the Laplace domain, we end up with capital I equal to C times SV minus V of 0. If you solve for capital V, we'll end up with capital V equal to 1 over SC times S domain I plus 1 over little s times initial condition of time domain V. Well, again, we're going to assume the initial condition is 0. If we make that assumption and we divide the current by the voltage, so V over I, you end up with the impedance in the S domain of the capacitor, which is 1 over SC. Alright, so impedance of a resistor in the S domain is equal to R. Impedance of an inductor in the S domain is equal to SL, S times the inductance. And the impedance of a capacitor in the S domain is equal to 1 over S times C, the capacitance. Let's do a couple of examples where we transform a time domain circuit into the S domain. Okay. Alright, so we're going to draw a series RLC circuit. Alright, so the input is going to be a step function with an amplitude of 2. The resistor will be 10 ohms. The inductor will be 0.1 henries. Capacitance will be 0.02 farads. And the value we're looking for is output voltage with respect to time. Alright, so let's take the Laplace transform of each component, or represent the component in the Laplace domain. So the input we'll call Vs of S. for source. And that'll be the Laplace transform of 2u of t, which is simply 2 over s. We represent resistors, inductors, and capacitors with an impedance. The impedance of the resistor is simply equal to the resistance, according to what we just covered. Impedance of an inductor is equal to S times the inductance. Impedance of a capacitor is equal to 1 over S times the capacitance. That's equal to 50 over S. So, if we're representing the circuit now in the Laplace domain, it keeps all the same element models from a sort of schematic drawing standpoint. But now instead of the values being in the time domain, now we represent them in the S domain. So the input is now 2 over S, resistor value is 10, or rather resistor impedance. Inductor impedance is 0.01 S, and capacitor impedance is 50 over S. And we're looking at the output voltage, which will now be in the S domain. That's it. It's really no big challenges with representing the circuit in the S domain. Just have to know how each element is modeled. Let's do one more quick example. We are going to again transform the circuit from the time domain to the S domain. Okay. So now we have a current source. You have 2 resistors this time. And then 1 capacitor, 1 inductor. Oops. The value of the resistors are 2 ohms and 5 ohms. Capacitor value is 0.1 farads. And the inductor value is 10 henries. And we represent the current input as a time-shifted delta function. Okay, so again, we're going to take each component, convert it into its S-domain model. The input current, so I'll say current source, is going to be equal to the Laplace transform of a time-shifted delta function. The Laplace transform of a delta function, just as it is equal to 1. Actually really straightforward, or a simple S-domain model. But because of the time shift, you have to look at the Laplace transform properties. You see that a time domain shift, you have to multiply the Laplace transform of the non-time shifted function by e to the negative at, where a is the time shift. Here the time shift is 2. You go to negative 2s times the Laplace transform of the delta function, which is 1. So it's just e to the negative 2s times 1. Now we're going to look at the S-domain model of the 2 ohm resistor, which we model with an impedance for a resistor is just equal to its resistor value. Let's do the same with the 5 ohm resistor. Pretty straightforward there. Let's look at the inductor. It's equal to S times L. And the capacitor. You go to 1 over S times the capacitance. And then we redraw the circuit. Alright, so the current source is represented with e to the negative 2s. The resistors just carry their values, because the impedance of a resistor is just the resistance. Capacitor will have an S domain value of 10 over S. Inductor will have an S domain value of 10S. And that's it. So again, we did the transformation. The circuit is now ready to analyze in the Laplace domain. We'll learn a little bit more about that circuit analysis in the next lecture. Again, this section was kind of straightforward. Just make sure you understand what we're talking about when we say impedance and how we can model the sort of everyday components that we analyze in transient circuits in the S domain. All right, thank you very much, and I encourage you to do some examples from the book. Bye.